All right, let's jump right into this explainer on chemical kinetics. In early chemistry, you probably spent a ton of time just figuring out if a reaction would happen at all, or trying to balance equations to see what the final products would look like. But today we're shifting gears. We're transitioning from simply asking if a reaction happens to investigating exactly how fast it happens, and more importantly, why. In this explainer, we're going to treat chemical reactions like a ticking clock, and we're essentially going to become detectives of time.
Here is what's on the agenda for today. We'll start with the speed of chemistry, move into the laws of reaction rates, and then decoding the reaction order. After that, we'll hit the math of time and half-life, temperature and collision theory, and wrap it all up with kinetics in real life. Let's get to it.
The speed of chemistry. So have you ever wondered why a diamond lasts literally forever, but an apple sitting on your counter rots in just a matter of days? Both are undergoing chemical processes, right? Both are constantly interacting with their environments. It's a really fascinating question, and the thing is, thermodynamics alone simply cannot answer it. We know both processes are technically happening, but the timescale is just wildly different. And that gap in our understanding, that is exactly why we need the science of chemical kinetics.
This brilliantly illustrates the distinction we have to make here. Think of thermodynamics as the rulebook. It tells us if a reaction is allowed to happen in the first place, specifically if the change in Gibbs free energy, or delta G, is less than 0. But here's the catch. The rulebook has absolutely no concept of time. Chemical kinetics, on the other hand, is the speedometer. It shows us the actual rate of change. It tells us how fast that feasible reaction will actually proceed to reach completion.
Well, how do we actually read this chemical speedometer? We define the rate of reaction as the change in concentration of any reactant or product per unit time. You're typically going to see this measured in moles per liter per second. Now, one absolutely crucial detail to keep in mind here is how we handle the math for reactants. Because reactants are being consumed, their concentration is dropping over time, right? So we calculate their change with a negative sign. This neat little mathematical trick ensures that our overall reaction rate always stays positive, representing a forward speed.
But speed can actually mean two very different things. We've got average rate and instantaneous rate. Average rate is the change in concentration over a measurable, finite time interval. It's exactly like calculating your average speed over a 500-mile road trip. Sure, it's useful, but it really doesn't tell you how fast you are going at exactly mile 200. Instantaneous rate is the true speed at a specific, infinitesimal moment in time, literally just like glancing down at your car's speedometer. Graphically, we find this precise rate by looking at the slope of the tangent line on a concentration versus time graph. And honestly, in kinetics, this exact moment-to-moment data is the stuff we really want.
Section 2. The laws of reaction rates.
Okay, so if you're in the lab and you want to change the speed of a reaction, you basically have 7 main levers you can pull. You can bump up the concentration or the pressure to force more collisions. You can crank up the temperature. You can increase the surface area, like, say, by grinding a solid chunk of a reactant into a superfine powder. You can add a catalyst to lower the energy barrier entirely, or introduce light for photochemical reactions. And of course, the physical nature of the reactants themselves always plays a baseline role.
Now, what's really cool is how we translate all those physical levers into a concrete mathematical equation. We call this the rate law, and it looks like this. Rate equals a constant, K, multiplied by the concentration of reactant A raised to the power of X, and reactant B raised to the power of Y. Listen closely here, because this is where students stumble all the time. Those powers, X and Y, they cannot be guessed just by looking at a balanced chemical equation. The standard stoichiometry, the big numbers in front of the molecules, does not necessarily give you X and Y. You have to physically run the experiment in the real world to find those exponents. There's just no way around it.
Section 3. Decoding the reaction order.
Let's clear up a major point of confusion right now, which is the difference between order and molecularity. Order of reaction is purely experimental. It's simply the sum of those powers we just talked about, X plus Y, straight from the rate law. Because it's based on real lab data, the overall order can be 0, a fraction, or even a negative number. Molecularity, however, is purely theoretical. It describes the physical reality of how many molecules are actually crashing together in a single elementary step of the reaction. And since you obviously can't have half a molecule colliding, molecularity is always a positive whole number, usually 1, 2, or 3.
And hey, here is a fantastic, absolute game changer of a trick for when you're taking an exam or analyzing a dataset.
By simply looking at the units of the rate constant K, you can instantly act as a detective and deduce the overall order of the reaction. No math required. If the units are moles per liter per second, boom, it's a zero-order reaction. If the units are simply inverse seconds, it's first order. If it's liters per mole per second, it's second order. The units literally give the secret away immediately.
Section 4, Math of Time and Half-Life.
Remember those instantaneous differential equations we mentioned earlier? Well, if we use a bit of calculus to integrate them, we get these beautiful, highly practical formulas called integrated rate laws. These equations are incredibly powerful. Why? Because they allow us to predict exactly how much of a reactant will be left at literally any future time t. All you need is the initial concentration, the rate constant K, and the time elapsed. It's like having a crystal ball for your beaker.
Which brings us to a very specific, highly important time frame, the half-life. Half-life is just the time required for a reactant's concentration to reduce to exactly half of its initial value. But here is what is absolutely mind-blowing about how this works for a first-order reaction. If you do the math, the half-life for a first-order reaction simplifies to exactly 0.693 divided by the rate constant K. Notice what is completely missing from that formula, the initial concentration. For a first-order reaction, the half-life is totally independent of how much material you started with. It takes the same amount of time to go from 100 grams to 50 grams as it does to go from 10 grams to 5 grams. Crazy, right?
Because first-order kinetics are so perfectly predictable, there's actually a fantastic mathematical shortcut you can use on exams. The time required for a first-order reaction to reach 99.9% completion is always roughly 10 times its half-life. So if the half-life is 2 minutes, you instantly know it will take roughly 20 minutes to be 99.9% done. It's just a really beautiful demonstration of how reliable these formulas actually are.
Section 5, Temperature and Collision Theory.
Now this next part is wild. We're going to see how heat fundamentally breaks the speed limits of our reactions. We call this the temperature coefficient. As a general rule of thumb, for every 10 degrees Celsius rise in temperature, your reaction rate doesn't just bump up a tiny bit. It literally doubles or even triples, a factor of 2 to 3. But why? Why does heat have such an explosive impact on speed?
The answer lies right here in the Arrhenius equation. You see, for molecules to actually react, they can't just lightly bump into each other. They have to crash together with enough force to overcome an energy barrier, which we call the activation energy, or EA. When you increase the temperature, you aren't just making the molecules move a little bit faster. You are exponentially increasing the fraction of molecules that possess enough kinetic energy to make that jump over the activation energy barrier. It's a massive, nonlinear leap in effective collisions.
Section 6, Kinetics in Real Life.
Okay, let's pull this heavy math out of the textbook for a second. Did you know all natural radioactive decay strictly follows first-order kinetics? This means we can use our integrated rate laws to date ancient artifacts. Imagine we dig up some ancient wood. Step 1. We know the half-life of carbon-14 is 5,730 years, so we easily calculate the decay constant. Step 2. We measure the radioactivity of fresh wood, let's say it's 15 disintegrations per minute, and we measure our ancient sample, which is dropped to 9. Step 3. We just plug those numbers right into our first-order integrated rate law and solve for time t. Just like that, using the exact formulas we've been talking about today, we can accurately prove that this wooden artifact is over 4,200 years old.
And honestly, that is the true power of chemical kinetics. By deeply understanding these concepts, by moving from simply knowing if a reaction happens to decoding exactly how fast and why, we aren't just doing abstract math on a whiteboard. We are uncovering the very timeline of the physical universe. Once you master these formulas, the world around you opens up like a readable clock, leaving you fully empowered to tackle any exam or any real-world problem you come across. So I leave you with this thought. Armed with these tools, what will you investigate next? Keep learning, keep questioning, and I'll see you in the next explainer.